Hey everyone. So we're going to start today by talking about Ohm's law, which describes the relationship between voltage, current, and resistance. I'm keeping everything color coded as much as possible. All three of these equations at the bottom are the same equation. If you remember basic algebra, you can divide both sides of the equation by the same variable and remove it from one side and shift it to the other. So I always try to remember V equals IR. Voltage equals current times resistance. And now that's voltage in volts, current in amps. I is the French word intensité, which the French physicist who developed the concept of amperage determined that for us. R in ohms, resistance in ohms. So if it's a 2K ohm resistor, that's going to be 2000 as an example. So it's a very interesting thing to remember. That's how I remember it. Very interesting to remember. And then from this, you can always translate it to these other forms depending on what you're trying to solve for. So we'll see how that applies in the next section of choosing a resistor for an LED. So, how to choose the right resistor for the LED that you're trying to light. We've got a simple tape circuit set up on one side. It's laid out in the schematic on the left. We're working with 3 volts DC, 2 AA batteries in series. We've put together a simple touch switch to show it in operation when it wants to. But how to figure out what that resistor should be. You need to know 3 things. We need to know the forward voltage of the LED, essentially how much power the LED wants in volts, the supplied voltage, so how much power we're supplying to the LED, and the amperage requirement of that LED. What does the current want to be to light it without burning it out? So knowing those things, let's see, the 2 volt LED, we're supplying it with 3, and it wants to be 0.015 amps or 15 milliamps. So if we kind of take that back into our Ohm's law values, if you remember R equals voltage divided by current, well, our voltage at this point needs to be the supply voltage minus the voltage of the LED. So the LED is using voltage, but it is providing no resistance. And because it provides no resistance, we can't figure its current or its values into this. We just need to subtract the voltage that it uses and then forget about it. So this equation becomes the resistance is 3 minus 2 divided by the current we're looking for. So resistance is 1 divided by 0.015, that's 15 milliamps. So the resistance that we're looking for to be spot on is 66.67 ohms. Now, finding a resistor of that exact value is going to be impossible, but choose the one that's closest and higher. So 100 ohms is pretty common. That's what we have set up here, 100 ohm resistor, and it lights itself without burning out. So following this equation, the resistor that you need is equal to the supplied voltage minus the LED's voltage requirement divided by the ideal current for that LED. So you can plug in your numbers, use Ohm's law, and figure out exactly what it is you're looking for. So now that we've talked about single resistors and figuring out their requirements in a single simple circuit, let's talk about resistors in series. To start with, we have an example circuit set up with 3 resistors, R1, R2, R3, with 6 kiloohms, 2 kiloohms, and 1 kiloohm of resistance. So that's 6,000, 2,000, and 1,000 ohms if we're plugging it into Ohm's law with a 9 volt DC supply. So we can start by figuring out the current that will run through these. And now that current will be the same no matter what the resistance value of each particular resistor is. It's based upon the total resistance of the circuit. So using Ohm's law, we can figure that the current is equal to the voltage divided by the total resistance, R1, R2, R3. That can be simplified into the current is equal to 9 volts divided by 9,000 ohms, which means that the current rating in amps is 0.001 amps, or that can be rewritten as 1 milliamp. So in this particular circuit, there is 1 milliamp of current running through the circuit, and so if we need to figure out the voltage drop across each one of these, we can now use that number in addition to the known values, and the resistance of each resistor will determine how much voltage is dropped across it. So in these examples here, since we know 0.001 is our current, no matter what the resistance is, we can plug in our resistances and figure out our volts. So each one of these, the 6K resistor, will be sucking up 6 volts of that 9, the 2K 2 volts, and the 1K 1 volt. And you can see that relationship where the higher the resistance, the more voltage will be dropped across that resistor. And the total of each one of these voltage drops across the entire circuit will always add up to the supply voltage. So let's figure out how we can use that to our advantage with voltage dividers. Okay, voltage dividers. We can see it in the schematic on the left here. It's a simple circuit that uses 2 series resistors to make an output voltage that's fractionally a part of the input voltage. Now the last circuit we looked at with just resistors in series, that is also a voltage divider depending on where you take out from in between the resistors. But we're going to simplify it to simply 2, and we're going to have our input voltage be the points measured from here and here, ground and positive. And when we say voltage out, we're talking about positive being drawn from here and voltage. So if you had a voltmeter and you measured these 2 points, that's what the output voltage would be versus the input voltage, which would be from these 2 points. We're going to look at this in an actual breadboard circuit in a little bit. So that relationship, when I say it's fractional, so the output voltage is equal to input times a fraction of the relationship between the resistors. So if our input voltage is 5 volts, R1 is 220 ohms, and R2 is 2000 ohms, we can see that equation becomes this, and then equals out to 4.5 volts. So if measuring out here with an input of 5, this will measure 4.5 volts. If we switch that relationship and we make R1 2000 ohms and R2 220 ohms, we can see that that actually balances out to be what was subtracted from the original equation, basically a half volt. So you can see that where those resistors are placed, what the values of those 2 resistors are in relationship to each other, will determine that output voltage as a fractional relationship between them. As a final example, if we made them both the same, we can then see that the voltage is halved. We're literally getting half of what the input voltage is as our output voltage, because if both of those resistors are the same, they're both accepting the exact same amount of voltage in Ohm's law, according to Ohm's law. Hence the voltage is halved across those 2 resistors. So here I've set up a couple of different circuits onto our breadboard. Just to explain what's going on, we're working from the ground and the 5 volt supply on the Arduino and bringing it over to the breadboard. I've jumped the negative to both sides and the positive to both sides with just 2 little pieces of wire, so that all the hots on both sides and all the negatives on both sides are all connected, so it doesn't matter which one they go to. We have 5 different circuits going on here. The first 2 are just simple series circuits, and we've got the schematic for both of those right here. The first one is simply a 220 ohm resistor in series with the LED. So we got the 5-volt hot side over here in the schematic and the ground on this side in the schematic, and we're using the breadboard like that here in both of these. Now the second one up is the light dependent resistor, which can vary from 500 ohms to 1 million ohms depending on the light. So if there's less light, like if I cover it with my finger, it'll go dimmer, and if there's more light, like a little flashlight, it'll get brighter. So we can use that to some advantage, but the next 3 circuits, the next 3 above that, are all voltage dividers. The first one, third one up here, is 2 220 ohm resistors creating a voltage divider. Now we've got one going from the hot to one of the rows here, and then one going from that same row back to ground. From that row, we've got our LED reaching back to the hot side on this side, just for visual sake. It could go to either way, but the short leg is pointing to the left as I knock it out of place. The short leg, the negative side, is to the left. The hot side, the long leg, is going into the red rail for the positive voltage on the right. Because we know in a voltage divider like that, we're dividing our voltage in half, and since we're working from the 5-volt supply, we know it's getting exactly 2.5 volts. So the red LEDs work perfectly at 2.5 volts. So if you really wanted to get right on, you can use a voltage divider. The next 2 above that, however, are slightly different. We're using a light-dependent resistor in the voltage divider with the LED. And in each case, we've got the LED going to a slightly different place. The first one, fourth one up here, we're taking from the divider and going back to positive on this side. And we can see that actually that means that it doesn't light in ambient light. On the one above it, we're going from the center of the divider back to negative. So depending on the orientation of the LED, it will depend on how it operates in ambient light. So the first one at the top, we can see it's on now, and actually when it gets darker, it'll get a little bit brighter. Just a tad. Just a tad. But the interesting part is when it's really bright, it goes off, which is the opposite of the one below it. So in very low light, the top circuit will light. In very bright light, the second to top circuit will light. And that's all dependent upon the light dependent resistor and where it is in the circuit and how you're bridging off from that portion of the divider to hot or to ground with your LED. And because this relationship always maintains a balance, a fractional relationship, as one of them increases or decreases, it will change the available voltage from that part of the divider. And we're just tapping into it in 2 different ways to affect the operation of it. So if you go back and do the math with Ohm's law, you can start to see why that works. Start plugging in these numbers. Remember, this 1 million, when it's bright, will be as low as 500. So plug in those numbers and see what you get, and see what happens to that voltage between those points, and see why the LEDs either go out or turn on.